In the last video, what we did is we worked out the equations for time dilation. So if you had two frames of reference, one that is moving with respect to another one, moving with some relative velocity v, then what we found is that the time measured by the person outside, delta t, of the time that's measured on the inside, delta t bar, then what you found is that they are related by this equation here, where gamma is 1 over the square root of 1 minus v over c quantity squared, or we like to use beta as v over c, so gamma is 1 over the square root 1 minus beta squared. All right. So there's this relationship between the time measured by someone who calls themselves at rest, and then the time of the person outside where they're moving with a relative velocity. Okay, so let's take a look at an example. So we'll look at example 12.1, where we have this subatomic particle called a muon, which is a lepton, a heavy cousin of the electron, and the muon is going to decay into an electron and a neutrino. And so what you have, well, actually two neutrinos, electron neutrino and a muon neutrino. So what you have and is this subatomic particle at rest. This decay will on average take about 2 times 10 to the minus 6 seconds, so 2 microseconds. So that's when it's at rest. That's why I'm calling it delta t bar. If I now want to measure what is the time that I would measure outside here of this muon moving by at a speed of, say, 3/5 the speed of light, then my measurement of the decay time is going to be gamma times delta t bar. And gamma, we said, was 1 over the square root of 1 minus v over c quantity squared times delta t bar. So that turns out to be 1 over 1 minus 3/5 squared, 2 times 10 to the minus 6, or that's 2 times 10 to the minus 6 divided by the square root, 25 minus 9 over 25. 25 minus 9 is 16. Square root of 16 is 4. So what we get is 5/4 of the decay time, or 2.5 times 10 to the minus 6 seconds. And so the time now takes longer. Time slows down, and it takes much longer, but from my perspective, when I measure the decay time of the muon. All right, so the next example is the twin paradox. I'm actually going to skip that. It's actually a good thing to read over, but it has a lot of complications with it in the fact that in the twin paradox, you actually can't avoid any sort of acceleration as the spaceships are speeding up and slowing down to go to different planets. And so instead what I wanted to do was to go over the Lorentz contraction. Okay, so I think this is item 3 in this section. And so basically what we want to do is look at lengths. We've already looked at what happens to time when we measure different times in different frames of reference. What happens to length? And so the particular example that the book uses is that you have a light source right here, and you have a mirror on the other side of the room, and so light now is going to go down to the end of the room, reflect, and come back. And so we're going to put this apparatus in some kind of car or truck, and then So what we find is that while this thing is sitting here, if you were standing on the inside of this truck, then the distance that the light moves is delta x bar, and it moves in a time of delta x t. So the time it takes for the light to leave the light bulb, bounce off the mirror, and come back would be 2 times the length divided by the speed, and light moves at the speed of light. It's in the name. So now the question is, what happens if we move this truck with a constant velocity? And so we still have our light bulb. But now the light has to travel a longer distance to catch up with the mirror, and then it reflects back, and by the time it gets here, it's now back at where the light bulb is. So now there's actually 2 times. So delta t1 is the time it takes to go down to the mirror, and delta t2 is the time it takes to go from the mirror back to where the light bulb is. So now there are 2 different times. So those times are delta t1 is the length that it traveled, delta x, plus the velocity of the car, the truck, whatever you want to call it, times delta t1 divided by the speed of light. For delta t2, it's the distance that it traveled minus the distance that the truck traveled minus the speed delta t2 over the speed of light. Okay, so now what we can do is we can just solve for delta t's. So if I go down here, delta t1 times 1 minus v over c is equal to delta x over c, which means that delta t1 is delta x over c minus v. I could do the same thing for delta t2, and the only difference then would be I would change the sign on the velocity, so it's c plus v. Okay, so now we'll look at the total time, delta t, which is delta t1 plus delta t2, which turns out to be delta x 1 over c minus v plus 1 over c plus v, like so. We can do a little bit of algebra, and what we get is c plus v plus c minus v over c minus v times c plus v, like so, and I get 2c delta x over c squared minus v squared. And if I now factor out c squared from the denominator, we get 2c delta x, c squared 1 minus v over c quantity squared. So that's pretty good. We're getting something close to a gamma. And I can cancel one of the c's, and so what I get is 2 delta x c 1 minus v over c quantity squared. Okay. Now from the time dilation formula, we know that we have this equation. So now if I put in my equation for delta x, I get 2c delta x bar. So that's the distance that it would travel if it didn't, if it was at rest. And then I have essentially square root 1 minus v over c quantity squared. Two over c delta x divided by 1 minus v over c quantity squared. So the two c's cancel. I cancel out a square root there, so I have delta x bar is 1 over the square root 1 minus v over c quantity squared, like so. And if I plug in the gamma factor, I get delta x bar is equal to gamma delta x. Okay. So what you see is that length is contracted. So the measurement of the length when it's at rest versus the measurement of the length when it's not at rest is going to be contracted. So, okay, let me repeat. This is the length when it's declared to be at rest. Since gamma is 1 over the square root 1 minus v over c quantity squared, and v is going to be less than c, that means in this case gamma is going to be greater than 1. But that means that my measurement delta x of 1 over gamma, that length at rest, means that delta x is going to be less than delta x bar. So my measurement outside of the truck shows a shrinking of the length as opposed to the person who's measuring it from inside. Okay, so what we're left with then are these two equations, one for length contraction and one for the time dilation. So if I write it out, in terms of this, length contraction and time dilation. So time stretches and lengths are contracted. Okay. So I'll stop here and we'll continue the discussion of this in the next video.